You know, our world is absolutely humming with invisible forces, things that hold everything together, from the atoms in your body to the galaxies in space. And today, we're going to pull back the curtain on one of the most powerful ones, starting with, well, a pretty dramatic example.
80 times a year. Just think about that. That is an unbelievable display of raw, natural power. But you know what? That's not just some random weather event. It's a massive electrostatic discharge. And if you can understand what's happening there, you can understand the very same force that's powering our entire world. So here's how we're going to do it. First, we'll dive into the electric universe to meet the main players. Then we'll figure out their rules of attraction. After that, we'll map out the invisible force field they create, feel the energy in the air, and finally, we'll see exactly why this matters for you and me.
Okay, let's get right to it. Before we can understand anything else, we have to meet the stars of the show. Electric charges.
So, what is electric charge? Well, think of it like mass. Mass is a basic property of matter that lets it feel gravity. Electric charge is just another one of those basic properties, but it lets matter feel an electric force. It's not something matter has, it's part of what matter is, and it comes in two basic flavors, positive and negative.
And here it is. This is the single most important rule of the game, and it is beautifully simple. Things that are alike, positive and positive or negative and negative, they push each other away. But opposites, they attract. A positive and a negative will always pull toward each other. That's it. This one idea is behind almost everything.
And what's really cool is that charge has to follow a strict set of laws. First, it's quantized, which is just a fancy way of saying it comes in tiny, indivisible packets. You can't have half a packet. Second, additivity. This one's easy. You just add them up to get the total. And third, conservation. This is a big one. You can't just create or destroy charge out of thin air. You can only move it around.
Okay, so we know what charge is and the basic laws it follows. Now let's see how it actually behaves out in the wild, how it moves through things, and how we can measure the forces between charges. So it turns out, not all materials treat charge the same way. In some materials, called conductors, think of any metal, the electrons can just wander around freely. It's like a big open party. But in other materials, insulators, like glass or plastic, those electrons are locked down tight to their atoms. They can't go anywhere. And this simple difference is literally the reason we can build circuits and control electricity.
Okay, now this looks like it came straight out of a physics textbook, I know. But stick with me because what it's saying is actually pretty intuitive. It's the official rule book for how strong that push or pull is between two charges. Basically, it just means two things. The bigger the charges, the stronger the force. And the farther apart they get, the weaker the force gets. And it gets weaker really, really fast.
And here's what it looks like as a formula. See the two charges, Q1 and Q2, right on top? When you multiply them, it makes the force, F, bigger. But look at the distance R on the bottom. As that number gets bigger, the force gets way, way smaller. That little squared symbol means that if you double the distance, you actually cut the force down to a quarter of what it was.
So we have these charges pushing and pulling on each other from a distance. But that brings up a really, really weird question. How? How do they actually do that across totally empty space?
I mean, seriously, think about it. There aren't tiny invisible ropes connecting them. So how does one charge even know the other one is there to be pushed or pulled by? The answer to this completely changed how we think about the universe.
It was this guy, the brilliant scientist Michael Faraday, who came up with a revolutionary idea. He said that every single charge creates an invisible field of influence that fills the space all around it. So, a second charge doesn't feel the first charge directly. Nope, it feels the field created by the first charge, right where it's located. It's a whole new way of looking at things.
And this is how we can actually see that invisible field. We draw these things called field lines. Think of them as a weather map for electric forces. If you were to drop a tiny little positive charge anywhere on this map, the lines and arrows would show you exactly which way it would get pushed.
And these maps follow some very simple rules. The lines always flow out of positive charges and into negative ones. Where the lines are all bunched up together, the field is super strong. And where they spread out, it's weaker. Oh, and they can never, ever cross. Why? Because you can't be pushed in two different directions at the exact same time.
Now, this electric field is more than just a map of forces. It's also a way of storing energy in the space around a charge. And understanding this stored energy is the next big piece of the puzzle.
The absolute best way to wrap your head around this is to think about something we all understand: gravity. You know how if you lift a bowling ball up high, it has stored energy, right? Gravitational potential energy. It wants to fall down. Well, it's the exact same idea in an electric field. If you push a positive charge towards another positive charge, you're pushing it up an electric hill. You're giving it electric potential energy. It wants to fly away.
So, electric potential is just our way of measuring the height of that electric hill at any given point. Every spot in an electric field has a specific potential value, and we measure that value in a unit you've definitely heard of, the volt. So when you see a high voltage, it just means you're at the top of a very steep electric hill. But here is the absolute key takeaway. A ball sitting on a perfectly flat table won't roll, right? It doesn't matter how high the table is. It only rolls if there's a slope, a difference in height. It's exactly the same with charge. A charge will only move if there is a potential difference between 2 points. And we have a name for that potential difference: voltage.
All right, we have talked about charges, forces, fields, and potential. We've been through a lot of physics here. So now, let's bring it all back home and see why this invisible world is one of the most important things in our everyday lives.
Let's go all the way back to that lightning bolt. Now we can see exactly what's going on. The clouds and the ground build up this massive separation of charge, which creates an incredible potential difference, a voltage of millions and millions of volts. That lightning you see, that's just all that built-up charge finally getting to roll down that enormous electric hill.
In that exact same principle, just on a much smaller, much more controlled scale, is what's happening inside the battery of whatever device you're using to watch this. The battery's job is to create a small, steady potential difference, a voltage, that constantly pushes charge through the circuits, lighting up your screen and making everything work.
And it's so easy to forget this, but we aren't just talking about engineering or gadgets. We're talking about one of the 4 fundamental forces of nature. The electric force is right up there with gravity. It's part of the very fabric of our universe. So what we've really done today is reveal the hidden architecture behind almost all of our modern technology. But it leaves you with a final thought, doesn't it? If this is just one of the invisible forces at play, what other incredible things are shaping our world right now in ways we can't even see?